Welcome back, students. In this lecture, we'll discuss a very familiar topic from your school classes, which is nothing but simple harmonic motion. Okay. So to start with, whenever we talk about simple harmonic motion, the first thing which comes to our mind is a simple pendulum, right? So to define simple harmonic motion, it is nothing but motion of a body to and fro about its mean position, such that the acceleration at any given point is directly proportional to the displacement from its mean position, and the direction of this acceleration is always towards the mean position. That is, its direction of acceleration is always opposing the motion, right? This is illustrative example of simple harmonic motion where we have a simple pendulum. These are the two extremes on left and right, and center one is the mean position, right? So as we see, as the ball moves from this point to opposite side, you can see that the motion is given by this direction, as the acceleration at all these instants will be opposing that. That is, the acceleration will be towards the center or the mean position. And also you can also see that as the distance from the mean position increases, the acceleration increases, which means that the maximum acceleration for a body will be at the extremes, and the maximum velocity will be at the mean of any SHM, body undergoing SHM. Okay. Now let's see that we can define SHM as a projection of uniform circular motion. So assume that there is a point P on the circumference of a circle of radius r, and it is moving along the circumference with a uniform velocity or a uniform angular velocity of omega. Okay, then if you take the projection of that particular point or that particular body moving along the circumference of a circle about the vertical diameter, which one is this, you can see that the motion of this projection is nothing but a to and fro motion about the equilibrium or the center. Okay, so here you can see this point dark circle is rotating around the circumference of a circle, and you can see that its projection is given by this blue circle. Okay, you can see the blue circle is a up and down motion or a to and fro motion along by the center, right? So this is again a simple harmonic motion. Okay, again if you try to plot this displacement of this projection, which is this blue dot, with respect to time, you can see that at the beginning the blue dot is at 0 or the mean position, then it goes all the way upward with passage of time, again it comes down, right? So you can see on the right hand side, this is the passage of time. So initially the position is at mean, as the time increases it moves up to the maximum, which is top, then it comes down to the opposite maximum, or we call it as minimum, which is a trough. Okay, again it goes up to the crest. So this is nothing but a simple harmonic motion, right? And let's see some terms related to simple harmonic motion, which is amplitude. So amplitude is nothing but the maximum displacement of the body from its mean position. Okay, and oscillation, one complete oscillation or one complete vibration of a body is called as oscillation, which means one crest and a trough together. Okay, this is oscillation. So whenever the half of this oscillation, which is either a crest or a trough, okay, this is called as beat. Okay, time period is the time taken, usually in seconds, for one complete oscillation. So time required for one complete trough and crest complete, right? And frequency is nothing but the inverse of time period, which is number of oscillations per second. Okay, or number of vibrations per second. The unit of frequency is SI unit is hertz, denoted by Hz. It is nothing but per second or 1 by second, right? Time period is always inverse of frequency. Now let's see the expressions for the displacement, velocity and acceleration of a body undergoing simple harmonic motion. Okay, so let's see that the body, this point is moving about a circle of radius r with an uniform velocity omega. Okay, so in t time it can travel an angular distance of about omega into t. Okay, so this angular displacement is nothing but angular velocity multiplied by time. So theta is equal to omega into t radians, right? Again, in order to obtain the position of or displacement of the body undergoing SHM, we want to find out what is this height at any instant t. Okay, so let's assume that this is a triangle. Okay, so this height is nothing but sine theta is equal to opposite by hypotenuse. This is again a, right? So opposite is equal to a into sine omega t or a into sine theta. So either you can call it as a, it is amplitude, or it is nothing but the radius of the circle. Okay, so I write opposite, which I can call it as y, which is the displacement of SHM. Okay, so y is equal to r into sine theta, where theta is omega t. Okay, again this is the first expression you have to remember. The displacement of body undergoing SHM is given by r into sine omega t. From here you can get sine omega t is nothing but y by r. Okay, so once you have displacement, you can also find out the velocity of this motion, which is nothing but the first derivative of displacement. So v is equal to dy by dt. Okay, so d by dt of r sine omega t. So we have r into omega into cos omega t. So this is the expression for v. But again, cos square omega t is nothing but 1 minus sine square omega t, which means that cos omega t can be written as square root of 1 minus sine square omega t. Also sine omega t is y by r, so substitute y by r in place of sine omega t. Okay, so you get omega into r into square root of 1 minus y square by r square. So substituting and solving, we get v is equal to omega into r square minus y square. Okay, this is another important expression. So you can see that the velocity is maximum when y is equal to 0 and its value will be omega into r. Okay, so the maximum velocity Vmax is equal to omega into r and it occurs at y is equal to 0. So y is equal to 0 is nothing but the mean position, which means that the body is at the starting point or at the mean position about which the body vibrates. So maximum velocity is always about the mean position. Okay, and in order to find out acceleration, what you have to do is you have to find the second derivative of displacement or the first derivative of acceleration. So acceleration is equal to d square by dt square, or it is dv by dt. So if you take the derivative of this velocity again with respect to time, we can get it as r into omega into minus sine omega t. Okay, which is nothing but minus r omega square into sine omega t. Again, what was r sine omega t? So r into sine omega t is nothing but y, right? So you can write acceleration is equal to minus omega square into y. From this expression, this is another important expression. So acceleration of a body is always equal to minus omega square into y, which means that it is acceleration is directly proportional to y, which is the distance from the mean position, and also the value of acceleration is always opposite to that of y. That's why we have a minus sign here, right? So the maximum acceleration can be obtained when y is maximum. So y is maximum at the farthest point, which is nothing but when y is equal to r. So maximum acceleration is always at the extremes and it is equal to omega square into r. Fine. So with that, let's see some problems. So the piston of steam engine moves with an SHM, which is the crank rotates at 120 rotations per minute. So n is given. From the n we have to find out omega, or the angular velocity or angular frequency. Okay, the stroke length is given, which is 2 meter, which means that it is the entire stroke length. So amplitude will be 2 by 1. Okay, now we are asked to find out the velocity and acceleration at a position when it is at a distance of 0.75 meter from the center. So 0.75 meter is nothing but your y. Okay, this is n. From here you have to find out omega, and stroke length, from stroke length you can get radius or amplitude. R is equal to half of this. Okay, so first of all we will find out the angular velocity omega. So 2 pi into n by 60. Okay, 2 into pi into 120 divided by 60, you get angular velocity is 4 pi radians per second. So the expression for velocity is at any point is v is equal to omega into r square minus y square. R is piston length by 2, which is 1. Okay, and y is 0.75 given in the question. Substituting that velocity as 8.3 meter per second. And also you have to also find out the acceleration at 0.75 meters. So it is minus omega square into y. So minus 4 pi square into 0.75, we get 118.4 meter per second. That was a simple problem for illustrative purpose, but keep in mind you have to remember the expressions for velocity and acceleration at any instant of time. Okay, now we have one more problem here. So there is a mass attached to two springs. You can see that there are two different arrangements. So in the first arrangement the springs are connected in parallel, and in the second arrangement the springs are connected in series. The spring constant of each of the springs is given 4 kN per meter and 6 kN per meter. Okay, and the mass in both the cases is same, which is nothing but 50 kg. Okay, and the initial displacement of 40 millimeter is given to the each of the mass, and then it is released, which means that r, or the amplitude, is going to be 40. Okay, 40 millimeters. So 40 by 1000, which is nothing but 0.04 millimeters, right? So what is asked here is to find out the period of vibration, which is time period of vibration, the maximum velocity, and also the maximum acceleration of the block in each of the arrangements. Okay, so it is to be understand that whenever there is a spring mass system, okay, and none of the other forces are acting on it, you can see that the system will always undergo a harmonic motion, simple harmonic motion, until it is in a frictionless world. Okay, and the frequency of vibration will be the natural frequency of the system, which is nothing but omega is equal to square root of k by m. So this is important. We will again come through this equation in the later classes. For time being, you can see that the natural frequency of a system, of a mass spring system, is always equal to root k by m, where k is the stiffness of the system and m is the mass in the system. Okay, now it is told that in the first arrangement the springs are in parallel. So when the springs are in parallel, the equivalent stiffness is k is equal to k1 plus k2, the sum of all the stiffnesses. So 4 plus 6, the equivalent stiffness is 10 kN per meter. Okay, which is nothing but 10,000 Newton per meter. Okay, the first thing you have to do is you have to find out the natural frequency omega n, or the angular frequency. So omega n is equal to root k by m. Okay, k is to be substituted in Newton per meter and mass in kilogram. Okay, then you will get omega in radians per second. Okay, so omega is equal to 14.14 radians per second. Once angular velocity is obtained, you can find out time period t is 2 pi by omega n. Okay, this is familiar to you. So you get time period is equal to 0.444 seconds. Okay, the next thing you have to do is you have to find out the maximum velocity. So maximum velocity is always at the mean position, and its value is xm into omega n. Okay, or r into omega n. Here r is 0.04, which is the amplitude, multiplied by omega n is 14.44. So you get Vm is equal to 0.566 meter per second. Okay, and again you have to find out the maximum acceleration, which is at the extremes, and its value is xm into omega square. Okay, or r into omega square, which is amplitude. So 0.04 into omega square you get AM is equal to 8 meter per second square. Okay, similarly when the springs are in series also, so when the springs are in series, in order to find out the equivalent spring stiffness, 1 by k is equal to 1 by k1 plus 1 by k2, which means that k is equal to k1 plus k1 k2 divided by k1 plus k2. So you can find out the equivalent stiffness by this expression. Okay, and you get this equivalent stiffness equal to 2.4 kN per meter, which is nothing but 2400 Newton per meter. Once you have the stiffness and the mass, you can find out the natural frequency as root k by m. Okay, you get 6.93 radians per second. Okay, so note that every time you have to substitute the equivalent stiffness in the equation. Okay, ke is to be substituted every time. Once omega is there, you can find out time period as 2 pi by omega. So time period in this case, when the springs are connected in series, the time period is more, which means that the body takes more time for completing a single vibration. Earlier the time period was 0.44 when the body is in parallel. In that case the stiffness was more, that's why the time period is more less than. Okay, now next one you have to find is maximum velocity. So maximum velocity is equal to r into omega, it is in the mean position, so xm into omega n, you get Vm is equal to 0.277, and maximum acceleration is always at the extremes and is equal to a into omega square or xm into omega n square, so 0.4 into 6.93 square. Am is equal to 1.92 meter per second square. So that's it. This is a simple expression or simple examples involving SHM. Okay, we'll see more examples in the coming lectures.